we have to relate, okay, now. So we have to now relate to mole circle. Yeah, so I'm going to take copy the image of the element H. And we are going to sketch mole circle, just a sketch. Okay. What we are trying to do down here is we have to ask ourselves, okay, okay, let me relate to mole circle first, okay, and see where we go from here, okay. So I'm going to do this in 3D, right? So this is our surface, this is our X. I'm going to call this surface over here Y, and this surface at the front is Z. Okay, so we'll declare down here the XY plane is the in plane. Okay, the XY plane is the in plane. So we're going to draw, sketch 3D mole circle. So I'm going to focus on the compression because I assume that the normal stress is compressive. So this is our normal stress. Okay, shearing stress element rotate clockwise, shearing stress element rotate anti-clockwise. Okay, so based on the stress state that we have written down, we know that stress Y and stress Z are at 0, and then we have our so this is our normal stress Z line. Oh, sorry, stress X, and I'm gonna make assumption that this is our shearing stress. This is our shearing stress. Okay. So what we are very sure is point Z is over here. That's our point Z. Okay. So we try to locate point X on mole circle from the element. So the element is going to rotate in a clockwise direction. So if we were to sketch our transformation, let me sketch our transformation. X, Y, A. When I say Y, my hand writes Z. So now we're going to check. So X, point X on the element is going to rotate in a clockwise direction. Okay, so this is our point X. Over here is our point Y. Okay, so from here we can draw our mole circle. We know that over here is our stress average line for the XY plane. So now we can sketch a mole circle now. Okay, so okay, so this circle over here, so I need to draw a horizontal line. Do apologize, we have done that first. So we know that this is for our XY plane. and it's the in plane. Okay, and then we are going to construct the other two circles, right? So the other two circles, you have one circle over here, right? And this circle over here represents the YZ plane. And this is your out of plane. And then the last circle I'm going to sketch. This circle over here. Oh, something went wrong. Do apologize. Okay. The last circle over here. This belongs to your XZ plane. Again, which is your out plane. Okay. So when we drew the XY plane, right, when we construct the XY plane, we just apply 2D Mohr circle. Yes or no? Right, we just apply 2D Mohr circle. We can get our larger circle. Whereas the X, Y, Z, and XZ plane, we have to apply 3D Mohr circle. But you realize that the maximum shear stress, okay, there are two things I want you all to see down here. The maximum shear stress, okay, over here. So this is our tau max, right? It is the biggest diameter, right? So the tau max we see over here is due to the tau max which is in the XY plane, right? Or tau max XY, okay, which is the in plane, right? And moreover, the principal stress A and stress B, right, are determined. Stress A and B are determined from XY plane, okay, the XY plane, Mohr circle. So what does this mean to us? Okay, what does it? So I've drawn for you 3D Mohr circle, right? So what does this mean to us? Okay, so this means applying 2D Mohr circle is sufficient to design a transmission shaft. You don't need 3D Mohr circle, right? Because when you apply the 3D Mohr circle in the YZ plane and the XZ plane to construct 3D Mohr circle, there's no added value information that's required. Okay, so that's why most of the shaft design, we focus on what? 2D mold circle. It's not necessary to go into 3D mold circle. Okay, so this is a point that I want to elaborate, and it's a very important point. Okay, I don't want you to have the impression that 3D mold circle is useless. Okay, it's not, but for this case, we only need to use 2D mold circle. Okay, and the reason why is these reasons. Okay, the principal stress are in the XY plane, right? The maximum principal stresses are in the XY plane, and maximum shearing stress is in plane. The outplane information are just redundant, okay, and useless. So now, if we look at the 3D mold circle now, or the 2D mold circle now, okay, so I'm going to construct. So before I go on, any question? I don't see anyone writing anything. Okay. So what we have just done is we look at the formula that we need to apply to design transmission shaft, right? Normal stress in the X direction, you need to focus on the bending moment. The torque, you need to focus, or the shearing stress, you need to focus on the torque. What is a very good result is the maximum normal stress is occurring at the furthest distance away from the center is at the radius. Likewise, the torque is the same, right? Furthest distance from the centroid, you have the maximum magnitude. And then we relate to mold circle. And while relating to mold circle, we just constructed 3D mold circle. And from 3D mold circle information, we realize that it's not necessary to plot the circle that is our plane, i.e. your YZ plane and your XZ plane. All the information that is needed is in your XY plane to design your transmission shaft. Okay. So with this in mind, we are going to derive a series of formula. Okay, we are going to derive a series of formula to relate the values or the stresses that we calculate to mold circle. Okay, to 2D mold circle. Okay, and also to apply the boundaries of the yield strength into the design of the shaft. Okay, so now let me quickly construct our mold circle. Okay, again, this is just a sketch. So this is our normal stress. And then this is our shearing stress. Okay. Element rotate clockwise. Element rotate anti-clockwise. Here is our 0. I'm only going to construct 2D mold circle over here. Okay. So this is our stress X, our stress Y, okay, stress Z. This is our shear line. Right. And then we realize that this is our over here. I'm trying to do similar like what we had before. There's our point X. There's our point Y. And then we have our average stress. Then from here, we construct our 2D mold circle.